Corrosion. We're all familiar with it, whether it's the rust on your car or the traces of pitting on facility equipment and structures. But corrosion is more than an eyesore. It has a serious impact on safety, operations, maintenance, and therefore profitability. Safety is, of course, the first priority. Bridges and walkways have failed, pipelines have exploded, and tanks have leaked hazardous materials into the environment, all because of corrosion. Also, the costs of corrosion are steep. To repair or replace corroded equipment or structures is expensive, not to mention the losses caused by downtime, contamination, and so on. By some estimates, these costs may exceed 4% of our gross national product. In other words, billions of dollars annually. Obviously, if corrosion is not controlled, it can cause serious problems. But to control it, we must understand it. We'll begin with the question, what is corrosion? In simple terms, corrosion is the degradation of a metal by reaction with its environment. This is a completely natural process during which metal is converted to its native state. In nature, for example, iron exists in the oxidized state of iron ore. The metal state is man-made, created by forcing large amounts of energy in the form of heat into the ore. But the laws of nature also dictate that iron must eventually revert to its natural, stable form, which brings us back to the subject of corrosion. If you analyze the rust on a piece of common iron metal, you'll discover that the rust is composed of iron oxide. If you analyze common iron ore, you'll find that it too is iron oxide. Iron, by corroding, has simply reverted to its natural form. Of course, different metals will corrode at different rates, and different types of environments will influence this process. But the fact remains, corrosion is nature's way of returning a metal to its more stable, natural form. We'll discuss some of the factors that influence the rate of corrosion in more detail, but in general, corrosion requires four things: an electrolyte, an anode, a cathode, and a metal pathway capable of conducting a flow of electrons. Here's how it works. An electrolyte is any medium capable of conducting an electrical current. The degree of conductivity is determined by the number of electrically charged particles, called ions, that are present. Salt water, for example, is highly ionized because it contains numerous ions of conflicting electrical charge. This also makes it highly corrosive. Plain water, however, contains nearly equal quantities of positive hydrogen ions and negative hydroxyl ions. Because they combine to form neutral atoms, plain water is less ionized and less corrosive than salt water. In addition to the electrolyte, the corrosion process requires an anode and a cathode. That is, two metal areas with differing potential or voltage. This difference in potential is what causes electricity to flow between them. These two areas, known collectively as electrodes, may exist as separate pieces of metal or as different points on the same piece of metal. In either case, it's important to remember that the degradation will always occur at the anode. And finally, a wire or other conductive path is needed to complete the circuit and enable the flow of electrons, that is, negatively charged particles, to move away from the negative charge anode toward the positive charge cathode. To demonstrate this electrochemical action, we've simulated immersion of iron and copper in plain water. The iron is the anode, the copper is the cathode. First, we'll focus on what happens at the anode. Because the laws of nature dictate that opposites attract, negatively charged electrons at the anode site are drawn toward the positively charged cathode along the metal pathway. This leaves detached, positive charged iron ions on the anode surface. These positive iron ions, called ferrous ions, are now free to combine with the negatively charged hydroxyl ions found in the plain water electrolyte. Together with the free oxygen found in the water, this combination results in ferric hydroxide on the surface of the anode. Ferric hydroxide is a common form of rust. Meanwhile, the negative charge electrons that have made their way to the cathode are attached to the positive hydrogen ions at the surface of the cathode. Here, the electrons enter the solution and combine with the hydrogen ions to form neutral molecules of hydrogen gas. If this process were to continue, the hydrogen would eventually create a film on the surface of the cathode, neutralizing its ability to assimilate any additional electrons. When the electron flow stops, it also stops the flow of ferrous ions because these two processes are concurrent. They cannot take place independently of each other. When this happens, the corrosion cell is said to be polarized. The difference in potential between the anode and cathode has been reduced, and the corrosion is effectively stopped. However, there is one more element that typically upsets this balance. That element is oxygen. When oxygen is present, several things happen. At the cathode, the hydrogen atoms may react with oxygen to form water. As they are dispersed, the cathode loses its protective hydrogen film and remains active. In other words, because the cathode will continue to assimilate electrons, the corrosion process is sustained. In this instance, the oxygen has depolarized the corrosion cell. In addition to the presence of oxygen, many things will affect the rate of corrosion. For example, the greater the difference in potential or voltage between the anode and cathode, the stronger the corrosive action will be. Areas of differing potential may occur on the same piece of metal for a variety of reasons. Inclusions in the metal, surface imperfections, orientation of the grain, localized stresses, lack of homogeneity, as in an alloy, or even variations in the environment may result in cathodic and anodic regions. Where two different types of metal are in contact, the anodic-cathodic relationship will be determined by their position on the galvanic series of metals. This standard list of common metals is arranged according to their relative tendency to corrode galvanically. In our definition of the galvanic series, the higher the metal appears on the list, the more readily it corrodes. It is considered to be anodic or active. The lower the metal appears on the list, the more corrosion resistant it will be. It is said to be more cathodic or passive. Keep in mind, however, that the key to determining which of two metals will corrode depends upon their relative position to one another on the galvanic series. Because it is higher on the series, iron is said to be anodic relative to copper. Therefore, if iron is coupled with copper, it is the iron that will corrode. However, when iron is coupled with zinc, the iron will act as the cathode. The zinc will corrode because in this relationship, zinc is the more anodic of the two metals. In other words, any metal can act as the anode or cathode depending upon the metal with which it is coupled. Conversely, the closer two metals appear on the galvanic series, the slower the rate of corrosion will be. The difference in their potential, in other words, is reduced, and the rate of corrosion will diminish accordingly. In addition to this difference in potential, the relative size of the anode and cathode will influence the rate of corrosion. If, for example, the cathode or cathodic area is especially large, the rate of corrosion at the anode will accelerate. Here's an example. These two large copper plates are bolted together with steel rivets. The copper is cathodic and quite large relative to the anodic rivets. The corrosion of the rivets will be accelerated as a result. Now the situation is reversed. The plates are steel and the rivets are copper. Of course, the steel is still the anode and the copper is the cathode, but the relative size of the regions has changed. Now, when the plates are submerged in salt water, the rate of corrosion slows considerably. Therefore, it's important to consider not only the relationship of the two metals that form the galvanic couple, but also the relative size of the anodic-cathodic regions. Knowing how different metals react to corrosive influences is essential and will help us understand the role played by environmental factors. As we've seen, corrosion is the natural degradation of a metal exposed to certain conditions. These conditions exist in many environments. Our demonstration model window was based on iron submerged in plain water, but underwater environments vary widely. The presence of chlorides, sulfides, ammonia, or other contaminants will affect the rate of corrosion. Even the temperature of the water and its rate of flow can influence corrosion activity. Of course, marine environments are particularly corrosive. This affects equipment or structures that are literally submerged, as well as those that are subjected to splashing and heavy sea spray. Even high concentrations of sea salt carried in the wind can accelerate the corrosion of unprotected metal surfaces at some distance from the ocean. Corrosion is also common underground because most soils contain enough moisture to act as an electrolyte, thereby providing a primary requisite for corrosion. The rate of corrosion underground is affected by various soil characteristics. The degree of compaction or aeration, the presence of bacteria, not to mention other foreign metal objects, will all influence corrosion activity below ground. Atmospheric corrosion is, in principle, similar to that which occurs underwater or underground, as long as there is enough moisture in the air to serve as an electrolyte. This moisture can be in the form of rainwater, dew, or fog. Other contaminants in the atmosphere will also have a strong influence on the rate of corrosion. Industrial environments, for example, are often characterized by pollutants such as sulfur compounds, nitrogen oxides, carbon monoxide, sulfur dioxide, and so on. These pollutants are particularly corrosive and must be considered when specifying any corrosion control system. Even rural environments may have heavy concentrations of organic and inorganic contaminants, such as oxygen, carbon dioxide, and ammonia that will accelerate corrosive actions. Obviously, some environments are more corrosive than others, but in general, it's accepted that moist air is more corrosive than dry, hot air is more corrosive than cold, hot water is more corrosive than cold water, and polluted air is more corrosive than clean air. The higher the acid level, the more corrosive the environment, and a saltwater environment is more corrosive than a freshwater environment. At this point, we've defined corrosion and looked at how different environments can affect the rate of corrosion. Next, we'll examine some common forms of corrosion. First, there's general corrosion. In other words, the corrosive reaction occurs generally across the surface of the substrate. Because this type of corrosion occurs at a more predictable rate, it is relatively easy to control. Localized corrosion, on the other hand, occurs only at specific points on the substrate. It's less predictable and can cause unexpected, even catastrophic failure due to localized loss of structural integrity. There are many forms of localized corrosion known to corrosion engineers. Some of the more common forms include galvanic corrosion, which occurs when two dissimilar metals are coupled in the same electrolyte, causing the anodic metal to deteriorate. Pitting corrosion, that results when corrosion causes deep penetration at localized spots along the substrate. Crevice corrosion is the attack of a metal in the crevices between different metallic objects or between a metal and a non-metallic material. Dealloying is a dissolution of the base component of a two-component alloy, for example, the dezincification of brass. This often leaves a weakened metal structure. Corrosion fatigue results when a metal that may already have experienced some corrosion is subjected to cyclic loads. The combined effect of metal fatigue and corrosion can cause failure much more quickly than either damage would cause individually. Stress corrosion cracking happens when corrosion is accelerated by tensile stress. And hydrogen embrittlement occurs when hydrogen atoms on the surface diffuse into the metal and become hydrogen gas. The expansion of these gas molecules may cause the metal to become brittle and fail. If there is a void in the metal, the hydrogen gas molecules may concentrate in that area and cause hydrogen blistering. In addition, physical influences and temperature influences can accelerate the corrosion process. Physical influences are the abrasive effects of any material, solid or liquid, whose constant movement across the surface of the metal hastens the damage caused by corrosion. There are many types of physical influences. Cavitation corrosion occurs when bubbles in a liquid constantly form and collapse, resulting in localized high pressure against a metal substrate. Fretting occurs when ongoing friction between two metal surfaces causes one or both to deteriorate. And finally, temperature influences can cause corrosion. When high temperature corrosion takes place, the electrolyte is a molten salt rather than being in an aqueous state. This brief overview of the corrosion process brings us to the heart of the matter. That is, how do we control corrosion? Corrosion is, after all, a natural occurrence, and complete prevention is virtually impossible. However, it is possible to limit or control corrosion by three primary methods. You could select a metal that is less susceptible to the corrosive influences of the environment in question. You might modify the corrosive environment itself. Or you could inhibit the possibility of any electrical current flowing between the anodic and cathodic regions. This last method, reducing charge transfer, is typically the most practical and can be achieved by using an appropriate protective coating. Essentially, coatings are formulated to protect the substrate from corrosion in three ways: as a barrier to corrosion, as a corrosion inhibitor, or as a sacrificial element in the electrochemical process. Earlier you saw how an electrolytic solution is required for corrosion to occur. We also looked at the way in which oxygen impacts the rate of corrosion. You probably can't eliminate moisture or oxygen from the environment, but a good barrier coating, properly applied, will prevent these elements from reaching the metal surface and minimize the likelihood of corrosion. Inhibitive coatings contain certain additives or pigments that have corrosive properties. These inhibitive pigments are partially soluble in moisture and work by different mechanisms, but essentially they provide a coating that is more stable than the metal substrate they protect. In the past, red lead and zinc chromates were common inhibitors, but due to environmental and health concerns, today's high-quality coatings contain more environmentally friendly inhibitors like zinc molybdate and zinc phosphate. And finally, some coatings are called sacrificial because they include metallic particles that are anodic. In other words, to a limiting extent, the metal particles corrode at a faster rate than the metal the coating is designed to protect. The most common example is a zinc-rich coating applied to a steel substrate. The zinc, being higher on the galvanic series than the steel, is the anode. It will be sacrificed. That is, the zinc will corrode in place of the steel. Furthermore, as the zinc coating breaks down, it leaves byproducts which further inhibit corrosion of the steel substrate. Obviously, a properly specified and applied coating system may be your best defense against the destructive effects of corrosion. Of course, corrosion control is not inexpensive, but experts estimate that control costs far less than replacing equipment or structures that have been degraded by corrosion. No wonder plant owners, specifiers, and applicators realize that corrosion control is an essential component of their maintenance program. Sherwin-Williams has developed a wide range of industrial maintenance coatings that are formulated to resist the most aggressive environments, ensure long-term performance, and are VOC compliant. Our protective coatings and extensive experience in corrosion control can help ensure the safety, productivity, and profitability of facility operation today and in the future.